So this is lecture 13, number theory. So chapter 3 is on quadratic reciprocity and primitive roots. So rather than doing a lot of the presentation in the book on primitive roots, which proves things in a little bit greater than generality than I really care for, what I've done is I've given you a guided series of homework problems that proves that the group Z mod PZ star is cyclic. So you can have a whole string of homeworks that show Z mod PZ star is cyclic. This means it equals the set 1 g squared g to the p minus 2. So there's some generated g of order p minus 1. And so you have a guided series of problems that prove this. What's nice is if we know the structure of this group, we can actually use this to do a lot of things. So there are several different ways you can prove results. Sometimes you can prove results by a direct computation. And this is an explicit enough depiction of what's going on that we can actually do these computations. So in the lecture on Friday, I go through some motivation for primes and arithmetic progression, where if we know what this group is, we can prove certain results. The results I gave you on Friday actually hold for more general spaces than just Z mod PZ star. They hold for Z mod NZ star. The proofs are just more involved, more advanced. This is a first course in number theory. This is a pre-core 300 level course. There is no need to prove things in full generality. If you are upset and want things in full generality, there's a huge swath of literature you can read. I'm happy to read it with you. I'm happy to talk about it with you. But in terms of just seeing what's going on, I don't think it's the best use of our time. Now, the big result in this chapter is quadratic reciprocity. I think I mentioned that Gauss has at least 8 different proofs of quadratic reciprocity to his name that are fundamentally different. And he was extremely proud of this result. It is kind of hard to just look at this result and see why we give a damn. Right? Okay, so I can determine whether or not this is a square by looking at whether or not this is a square. Why do I care about stuff like this? So what I thought I would do today is prove a couple of results and give you some sense of why we care about whether numbers are squares, and just show how this connects to things in number theory. So we're going to do most of chapter 3 that I'm going to cover today. The other parts you are welcome to read at home, or you can look at other sources if you want to see things in greater generality. But this will give you a sense of what's going on. As of now, I'm not going to give the proof of quadratic reciprocity. If you want, I can say it's because there are so many proofs, I don't want to single out any proof over all others, and the other proofs would feel bad that they're being ignored. It's just a question of what do I think is the most important thing to see in the first course of number theory. And what I want to do instead is show you why we care. So we want to study, does x squared congruent to a mod n have a solution? Usually we will restrict ourselves to the case when n is a prime. So we talked a little bit about this in the past. We talked about how if we were doing things over the reals or the complexes, we have the fundamental theme of algebra if we go over the complexes. A polynomial degree d has exactly d roots. They may be repeated, they may be complex, but there's no mysteries. We showed that things can be very different if n is not prime. So for example, x squared congruent to 1 mod 12. How many solutions? Four. There's 4 solutions. X equals 1, 5, 7, or 11. So we have a polynomial degree 2 having 4 solutions. It seems a little bit bad. So some of your homework problem was to say, well, if this one has 4 solutions, maybe another polynomial has fewer solutions, and maybe things balance out. Maybe the roots are somehow distributed among the different polynomials. And there are results along those lines in terms of how things are distributed. And so the solution keys talk about something like that. But frequently we don't care about what's happening on average. We care what's happening for the problem we're studying. Now if this is a prime, it's very different. This will then have exactly 2 solutions. And so things will be very different in that case. And so what we're going to define is A on P. This is the Legendre symbol. And whenever I write P, if I don't say otherwise, P is a prime. This is going to be 1 if A is a non-zero square mod P. It'll be 0 if A is congruent to 0 mod P. And it'll be -1 otherwise. So the way the Legendre symbol is defined, the bottom is a prime. You can generalize the Legendre symbol to when the bottom is not a prime. Maybe it's a prime power. Maybe it's a product of distinct primes. Or maybe it's just some general number. And eventually you can go from the Legendre symbol to the Jacobi symbol. Again, for a first course, I don't really think if it's worth going into this. But it's worth knowing that it's out there. Okay. And so the question is, why would we care about something like this? This actually goes back to the first homework problem you got. Or the first real homework problem, not counting, reading the assignment and telling you what you want to get out of the course. So there was exercise 1.10. There was three sums of squares being a square. Find a sequence of consecutive numbers, the sum of whose squares is a square. So we want a sequence of consecutive integers such that the sum of their squares is a square. And we know the following fact. If we were to sum n goes from 0, let's do k goes from 0 to n of k squared, this is n plus 1, 2n, I think minus 1, 6. Or is it 2n plus 1? 2n plus 1, 2n plus 1. So this is a nice formula for sums of squares. Now that I've given you the formula, you can prove this by induction. And so if I want to sum consecutive squares, I could look at the sum k goes from 0 to n of k squared minus the sum k goes from 0 to m of k squared. And this would be n plus 1, 2n plus 1 over 6 minus m plus 1, 2m plus 1 over 6. And the question is, can I find a choice of n and m such that this is a square? Okay? Or we might say, fix m. Let C sub m be m plus 1, 2m plus 1 over 6. Find n and y such that y squared equals n plus 1, 2n plus 1 over 6 minus cm. So what we could do is we could try to solve the problem. We could first fix m equals 0, m equals 1, m equals 2, m equals 3. And see what we could do. We might actually want to take m not to be 0. Well, actually, yeah, m is 0 is fine. And then that would just mean that there would be no term over here. And so this is an equation to solve. It turns out that if I look at n as my variable, what's the degree of the right-hand side? 3. It's a cubic. So it turns out that this is an elliptic curve. So can everybody remember the definition of the Legendre symbol? Right. We just watched Finding Dory this weekend, and that was on short-term memory. So just making sure. Okay. So elliptic curve. You can often write it as y squared is x cubed plus ax plus b. And I'm basically doing some changes of variables to eliminate the x squared coefficient. I'm doing some things to make the leading coefficient be 1. I'm not going to go into when you can do all of this. But an elliptic curve is something like this, and we want to study this. And it turns out that there is an incredibly rich structure to something like this. We're about to go into cryptography. So we will do RSA, which for years was the gold standard of cryptography. elliptic curves are also used for cryptography. And it turns out that there is a group that you can associate to elliptic curves. And very similar to what we did on Friday, we want this global-local relation. We want to take some local information and build up a global object, and then use that global object to understand what's going on. This is how we did with the Riemann zeta function. This is what we did with the Dirichlet L functions. If we looked at information at each prime, we had this Euler product, we multiplied them all together, it gave us this function. And then by understanding this function, if you take the limit as s goes to 1, the zeta function blows up. There's infinitely many primes. And some of their reciprocals diverge like log x up to x. Well, looking at its value at s equals 2, you get that the sum of 1 over n squared is pi squared over 6. This proves there's infinitely many primes because pi squared is irrational. So building these global objects, this is one of the big ideas in modern number theory. And so I want you to at least leave this course with a sense of what goes on. So we want to find all integer solutions to this. Or more generally, we want to find all rational solutions to this. This is an extremely hard problem. Let me give you a quick sense of why there is such a beautiful structure to this. If I just look at a cubic, a cubic might look something like this. Okay? And so now, if I want y squared to be a cubic, are there any values in through here that I could take for y? Should I be able to find a y that squares to this number? Yeah, just take the square root. What about a y that squares to this number? No, because that's negative. So if I square over here, I'll have no solutions. Over here, I'll have no solutions. And I'll get something that looks roughly like this. Something like this. That's going to be what the curve y squared equals x cubed plus ax plus b looks like. Imagine I have 2 points on the elliptic curve with rational coordinates. So 2 points, rational coordinates. I can draw the straight line connecting them. Let's give them names. We'll call this one P. We'll call this one Q. And in a flash of insight, I will name this point R. Hi. What can you tell me about the line connecting these 2 points P and Q? What can you say about that line?
Its slope is rational.
Its slope is rational. What else can you say about that line? Not only is its slope rational, its intercept is rational. So how many of you remember your point slope, point forms, all that stuff from many, many years ago? You can calculate the slope by looking at y2 minus y1 over x2 minus x1. The slope is rational. And so with a little bit of work, you can see then the equation would be y minus y1 equals slope x minus x1. Everything is rational, so when you expand out, it's going to be rational. So you can write this as y equals mx plus b. Everything is rational. Well, now when I go over here, if I take y and replace y with mx plus b, I would get mx plus b squared minus x cubed minus ax minus b. Or maybe I want to do it the other way around. So let's do the other one. X cubed plus ax plus b minus mx plus b squared. Can somebody give me one root of this equation where this equals 0? Where is one point where this will equal 0?
P?
Yeah, P. So x1, the coordinate of P, the x coordinate of P has to be a root. So this would be the point x1, y1. Similarly, x2, y2 would also have to be a root. So then there's a third root left. Everything here is rational. These are rational. When I multiply everything out, the the product of the roots is going to be the constant term here and all that stuff. What can you deduce about R?
That's also rational.
Also rational. So I am using R for root, not R for rational, but it turns out they both work in the English language. So on an elliptic curve, if you haven't seen this before, if you had to define what it means to add 2 points, what would you say P plus Q should equal?
Negative R.
Who said that? Yeah, I said if you hadn't seen this before. So you've seen this before. If you hadn't seen this before, what would you say P plus Q should equal?
R.
But doesn't it seem natural to say P plus Q should be R? It turns out you define P plus Q to be negative R, the reflection down here. I'm not going to go into why that's the better definition. But it turns out if you do this, you actually have a group law on the elliptic curves. You have a group structure. The set of rational points has an addition operation. You have this commutative associative relationship. You have identities. It's a little bit interesting to think where's the zero element. I'm not going to get into that. But there's an incredible structure about this. Why am I doing this? We're about to go into RSA. We're going to spend a lot of time on RSA. It's wonderful mathematics. RSA is based on essentially the group Z mod PZ star or Z mod PQ Z star. It's based on those groups. These are nice groups. But maybe if I use a more complicated group, I can have a more secure crypto system. And again, to get a sense of where things go, the group structure here is a lot harder than the group structure on Z mod PZ star. And the hope is that this will thwart people trying to crack your codes. So it turns out I can build an elliptic curve from this. And there are lots of results about when something like this has rational solutions, or even stronger, when it has integer solutions. It is very hard to find integer solutions to this. Any Simpsons fans here? It's getting harder and harder to get a yes when I ask this question. All right. Anybody ever watch the Halloween specials? Those are often good. There's a Halloween special many years ago called 3D Homer, where Homer falls into the third dimension. Anybody remember this one? Back then, this was an extremely expensive episode to make, and Homer scratching his butt and saying, geez, I feel like I should be doing something here. And this was just a gag about how expensive it was to be doing this animation. And you see a lot of math floating around in the background. One of them is an almost counterexample to Fermat's last theorem, where the numbers almost work, but they just barely fail. It is a hard problem to talk about when there are solutions. So in mathematics, whenever we have something that's really hard, we look at something that's a little bit easier. And so trying to solve y squared equals x cubed plus ax plus b, this is really hard to find out where they're perfectly equal. What might be an easier problem related to things we've been looking at? What could we look at instead of solving this exactly?
Mod something?
Yeah, mod something. What should we do mod? Mod what?
Maybe a prime.
Mod p, mod prime. And so this is going to be our local data. And the idea is maybe it's a lot easier to solve this for each prime, and then somehow take that and build up some information. So again, a huge part of this course is we don't have any material we must cover. I want to talk to you about how you should think about problems, heuristics. How many pairs x and y do we have? So how many pairs do we have?
E squared.
So we have p squared. So we have p squared pairs x and y in z mod pz cross z mod pz. This means each component is in z mod pz, and we are allowing 0. So I'm not looking at z mod pz stuff. Okay, somebody give me an upper bound on the number of solutions this could have mod p.
P squared.
P squared. Give me a lower bound. 0. So the number of solutions is somewhere between 0 and p squared. Any thoughts on where you might put it between 0 and p squared? So this is a problem you have not seen before. This is deliberate. I'm putting you on the spot right now.
They're FDO.
Do you think it's really as high as p squared?
Probably not.
So do you think, so what I really care about is I care about the exponent. Do I really think the exponent is high as 2? Well, for something like that, it means no matter what x I take, essentially all the y's are working. If I take a generic x, how many y's do you expect to work on average? So 1? Okay, why 1?
Seems like a good number to start
Seems like a good number to start with. Can someone give me some thoughts based on what we've read in the chapter on why 1 might be a reasonable guess? How many solutions should this have at most? Y squared equals something. I'm asking how often is this a square? How many solutions should that have at most? It should have at most 2. Is every number a square mod of prime? No. So if I look at, say, z mod 3z, and does any number square to 2? No, 2 is not a square. 1 is a square. And so what we're seeing here is of the non-zero numbers, half the numbers are squares and half the numbers are not squares. This is a really crappy data point. All right, let's take a larger prime. Do you want to do 7? Skip over 5? Sure. So we have the numbers 1, 2, 3, 4, 5, 6. You know, I'll put 0 as a special thing all by itself, and here's n. Here's n squared. 1 squared is 1, 2 squared is 4, 3 squared is 9, which is 2. What's 4 squared? 2. I can actually get that faster because 4 is the same as negative 3. And I've already calculated, and the negative sign is going to, so it's going to just be 2, 4, 1. So we see that 1, 2, and 4 are all square. Oh. 1, 2, and 4. I'll put them in a square to know that they're squares. All right? So 1, 2, and 4 are squares. 3, 5, and 6 are not squares. It turns out half the numbers are squares and half the numbers are not squares. Can we prove this? This seems like a nice conjecture. So, conjecture. Half the non-zero elements are squares, mod p. We call these the quadratic residues. The other half aren't, and these we'll call the quadratic non-residues. Yes?
Sorry, I might be missing something, but why is 2 a square?
What's 3 squared?
Oh, it's 2 square mod 7.
It's mod 7.
Okay, okay.
Yeah, everything here is mod 7.
Okay.
So 1, 2, and 4 do have numbers that square to them. 3, 5, and 6 do not. So the notation is we'll say a non-zero number is a quadratic residue if it's a square, mod p, and or whatever we're looking at, and it's a non-residue otherwise. And from 2 data points, it seems reasonable to conjecture that half the numbers are squares and half the numbers are not. Yes?
Are we allowed to use the fact that z mod pz star is a cyclical group?
I would love to use that result and not go through the argument in the book. There is a reason why I'm giving you a string of exercises. There's 10 problems this week. I think 7 of them, or 6 of them, something like that, are devoted to proving that z mod pz star is cyclic by breaking it up into lots of small little cases. And I'm not proving it for the most general choice of primes. I'm doing it for a very special set of primes, but it's enough to give you a flavor. And if you want to push it to the greater generality, you can. The book actually proves that if n is equal to 2, 4, p to the k, or 2p to the k, that the corresponding group is cyclic. I don't want to go into that level of proof. I'm quite content to just say z mod pz star is cyclic. So again, I'm trying to motivate why we care about quadratic residues. So I'm using elliptic curves as a motivation. We've just discovered this interesting fact that maybe half the numbers are quadratic residues, half are not, and that could help us in terms of estimating the number of solutions to this. we'll be using that as local data to build up a global object, which we then hope can have some control, some understanding. Okay.
Well, we know each quadratic residue has at least two things that multiplies to it.
Okay.
Because they both have like, if k multiplies to it, mod p, then also negative k multiplies to it, mod p.
Okay. So,
You just got to prove that like there aren't any repeats.
right, okay. So what we're basically saying is, then you also have to prove that no number is equal to its negative. Right? Which is going to be fine because p is, so we're going to assume p is big. Assume p is big. What do you think I mean by big? Yeah. At least 3. The reason is 2 is a troublesome prime. Because if you look at z mod 2z, well, there's only one non-zero element, which is 1, which is a quadratic residue. So the theorem is actually false for p equals 2. Can we just say that 2 is not a prime? No. We're not allowed to do that. 2 is a special prime. And for elliptic curves, it turns out 3 is also a special prime, and they cause incredible heartaches. Because of 2 and 3, my PhD thesis is probably 40 pages longer than it would have been otherwise if 2 and 3 were just good little primes like 5, 7, and all those other ones. So let's assume p is big. Z mod pz star we know is cyclic. It's 1 g squared g to the p minus 2. We're trying to show a number has a square root mod p. Alright, so consider g to the m, which is an arbitrary element. What are the two possible cases on m? Odd or even. So case 1, m even, so m equals 2k, we have g to the m is g to the 2k is g to the k squared. And we have a square root. Right? The square root is going to be gk and negative gk. And you can just show that the two are distinct. So square roots are g to the k and p minus g to the k. So, okay, we've handled the case of m even. So, case 2, m equals 2k plus 1 is odd. So now, g to the m is g to the 2k plus 1. We want to show that this can't be a square. How should we do this? So how could we show that this is not a square? There's a couple of ways we can go. Any thoughts on something we could try?
Contradiction.
I'm sorry?
Contradiction.
So contradiction. So we could assume it's a square. So what would it mean for it to be a square?
It exists some element in the group which turns itself equals to
Okay, so then that would mean if it's a square, then g to the m would have to equal g to the l times g to the l. We don't know initially that it's something in the form g to the 2l. We know it's equal to the square of an element in our group. Because our group is cyclic, we can write it as g to the l times g to the l, which is g to the 2l. So now g to the 2k plus 1 equals g to the 2l. So either k is larger than l or l is larger than k. And eventually, you're going to get g to a certain power equals 1. What power of g equals 1?
minus 1 plus 1.
I'm sorry?
P minus 1.
P minus 1. So this would give g to the 2 k minus l plus 1 equals 1 mod p. we have g to an even power, g to the p minus 1 is 1. So you want to think, is this going to be a contradiction? Well, there's no smaller power of g that equals 1. Otherwise, we would have 1 repeated twice. So we know that the only powers of g that can be 1 are multiples of p minus 1. If p minus 1 is even, what's true about multiples of p minus 1? Even. So this is a contradiction. So contradiction on order of g is even. And that finishes the analysis. The other way we could have done this is we could have looked at the equation g x. So I'll just put it very briefly here. You could have tried to look at x to the p minus 1 over 2 is congruent to 1 mod p. And tried to count solutions to this. And we know we've got p minus 1 solutions coming from these, so there can't be anything else. So you could try to use this. I'm not going to go through the details. We've already got a proof. But here's another way to try to attack things. So we know that half the numbers have square roots. Not surprisingly, those are the ones that are g to an even power. The square root is exactly what you would expect. Just divide the exponent by 2. So the even exponents are fine. The odd exponents do not have square roots. So we now know that as long as p is at least 3, half the non-zero numbers are squares, half the non-zero numbers are not squares. Wonderful. All right, so again, now let's go back to what we're trying to do. We're trying to understand how many solutions there are to this equation. This is the motivation for why we care about this Legendre symbol. Why are we spending an entire chapter of the book talking about quadratic reciprocity? Well, if I choose, x, I look at x cubed plus ax plus b. It's either a square or it's not. If the word were nice, how often would it be a square? Half the time. And if it's a square, how many solutions are there? Always 2?
At least.
Well, we just showed that a non-zero square
Yeah, I guess this one's 2.
has exactly 2. So if this is a square, how many solutions are there? Except, there's one thing you have to be careful about. Yes? If it's 0. Okay? So now when we're trying to look at what's going on, you're building on intuition. So if x cubed plus ax plus b is a non-zero square, 2 solutions. If is 0, how many solutions? 1 solution. And if it is not a square, 0 solutions. And if we guess that each one of these happen, that this happens essentially half the time, and that's the 1 over leftover case, then we would get on average there's 1 solution. So we would expect the number of pairs to be of size p. Expect number of pairs of size p. What does this look like over here?
The Legendre.
Doesn't this look a lot like the Legendre symbol? Is it exactly the Legendre symbol? Yeah.
Mod 3.
Um,
Look, you could treat it as 2 be negative 1. Or no, that'd be reverse.
yes, it's not quite one. There's something better than mod 3. Yes.
Plus 1.
Plus 1. Right? I really understand adding 1 well. It's one of the things I can do. I prefer often to multiply by 1, but if I had to, I can add 1. So what we're really showing here is that if we want to count the number of solutions, this is related to the Legendre symbol. So if we look at x cubed plus ax plus b on P and add 1 to that, this equals the number of y such that y squared equals x cubed plus ax plus b mod p. So we're beginning to see now where the Legendre symbol comes into play. And so if we now sum over all x, we would get, the sum of 1 over all x. That's not that bad, that's just p. And then we would have the Legendre sum. We expect that the number of solutions is p. So we study what's called AP, which will be p minus the number of pairs of solutions mod p. So what we're doing here is a common thing in mathematics. We know what we expect the answer to be, so we subtract the actual answer from the expectation, and we look at the fluctuations. And so this is going to become p. Now when we sum this all over all x mod p, what's the sum of 1p times? That's just going to be p. And then we'll have plus a sum, x goes from 0 to p minus 1, of x cubed plus ax plus b on p. The p's cancel, and you get negative the sum, x goes from 0 to p minus 1, of x cubed plus ax plus b on p. So here's the Legendre symbol. This is giving me my APs. And we use these APs to build an L function. So LSE will be a sum of an over n to the s. I'm not defining how you figure out what an is if n is not a prime. I'm not proving that there's also a product representation as a product over primes. You would do this in a more advanced class. This is meant to just give you an inkling of where things go. This is an introduction, that's the sequel. But what it's telling you is this Legendre symbol is useful. And so a huge amount of my thesis and a lot of my papers deal with trying to execute these sums. And so knowing things like quadratic reciprocity, knowing things about how to compute these things, there's a lot of stuff you can do here. And it's an absolutely wonderful subject. So, again, in the book they state quadratic reciprocity, it's a wonderful result, but it's not necessarily clear why we need it. At least now we have some idea of why we might care about these quadratic characters, why we might care about these Legendre symbols. They can help us count solutions to things. Now the question is there a way to actually execute these sums? It turns out there is. It's much easier if you didn't have the x cubed. If you just had ax plus b, it's extremely easy. If you had a quadratic, it's also extremely easy. If you have a cubic and higher, it is almost impossible. Unless you cherry pick your coefficients. And so if you cherry pick your coefficients, you can often do great things. But there's a lot of stuff going on here. So this gives us some sense of where this all goes, why we care about, is a number a square? This goes back to the very first problem from day one. Is there a set of consecutive numbers whose squares sum to a square? That's actually asking about points on an elliptic curve. So in terms of counting how many points there are, a lot of you wrote computer programs to investigate. I know a little bit more about elliptic curves. There's an advantage of having Andrew Wiles as one of your mentors. I know exactly how to determine what solutions there are to this elliptic curve. I can write down all the solutions. I can tell you if there are infinitely many, if there are finitely many. There's a lot of great stuff we can do about this. So that problem was not just a make-work problem. It's really an introduction to a vast set of mathematics. Okay. Any questions on what we've done so far? Okay, so we're trying to lead up to the statement of quadratic reciprocity. And so the whole point of quadratic reciprocity is you want to figure out, is this number a square modulo this number? And I say, screw that, I don't want to do that. I'm going to figure out if this other number is a square modulo this other number. And we just keep playing these alternating games. It's very similar to the Euclidean algorithm. So quadratic reciprocity, and I'm only going to do a special case. P, Q are odd primes, What's the advantage of P and Q being odd primes?
It's not 2.
It's not 2. So then you get P is the square modulo of Q is going to be -1 to the P minus 1 over 2, Q minus 1 over 2, QP. Right. So this is quadratic reciprocity. What's nice is this is an extremely well understood factor here. And in fact, if either P or Q is 1 mod 4, then this will be an even number, and this number will just vanish. And the whole point is to calculate is P a square modulo Q. Well, first of all, I can reduce P modulo Q, right? So let's say I wanted to do
Does P and Q have to be distinct?
they don't, well, but I mean, if they're not distinct, you're asking is 0, which you don't really want that. So let's take 27. Oh, it's always going to be.
You can use 73.
I'm sorry?
You can use 73.
I can use 73. Yeah, but there's going to be some issues with this. Okay, so let's do it the other way. So let's look at 73, and I was doing 37. So I want to know, is 73 a square mod 37? Well, I can just calculate all the numbers mod 37, square them, and see if it works. Or I can use quadratic reciprocity. 73 minus 1 is 72. Is that a multiple of 4? Yes, that means I don't have to worry about this -1 factor. So the first thing is, I can reduce the 73 mod 37. So what's 73 mod 37? I'm sorry?
Is that -1 mod 37? Like it's 36, isn't it?
Well, 36, so this would be, so this is now 36 37s. Right? I'm sorry?
Perhaps 73 is not a great option.
Well, so we're wondering, is this a square? So this is getting a little bit harder to study, but it turns out that the symbol is actually multiplicative. And I can write this as 6 over 37 times 6 over 37. Because if 6 is a square, so is 36. If 6 is not a square, well, since I have it twice, it's going to be to an odd power, right? And an odd power to another odd power will be to an even power. So I just have to understand 6 and 37. And then this is the same, 6 on 37. This would be the same as 2 on 37 and 3 on 37. And I've got to figure out how to deal with 2, because 2 is an even number, and I'm assuming I have odd primes. So you've got to figure out what's going on with 2. But for 3 and 37, we can figure out what that is. Well, what do I do for 3 and 37? I use quadratic reciprocity. 37 minus 1 is 36. That's a multiple of 4. I don't have to worry about the -1s. This is the same as 37 on 3. Well, I only care about 37 mod 3, which is going to be 1. And so that's a 1. Okay. So I would just have to figure out what 2 is. Now, of course, for this particular problem, I can stop. Is it hard to figure out, is 36 a square mod 37? Can somebody give me a number that squares to 36 mod 37? 6, right? So, really, there's no point in continuing to do this analysis here. At this point, this is either +1 or -1. I'm squaring it, great. It's going to become +1. But this just shows you how it goes. This is very similar to the Euclidean algorithm in terms of how you keep doing this with this flipping. You should probably be able to show every 2 steps you decrease by a factor of at least 2, it's going to run in logarithmic time. You can very quickly determine if a number is a square. Okay. I'm sorry? No, it's really nice. So the last thing is, how would you prove quadratic reciprocity? So hopefully, we now understand that quadratic reciprocity allows us to efficiently calculate things. We need to figure out what to do with 2, but deal with that later. So we have Gauss for the proof of quadratic reciprocity. We haven't done Euler in a while. Euler should definitely be in any conversation. So we have Euler's criterion. A on P is equal to A to the P minus 1 over 2 mod P. Just making sure I write this wrong, because if not, I will be in huge trouble. Okay, great. So what he's telling us is there's an easy way to calculate if A is a square. Just calculate A to the P minus 1 over 2 mod P. We know that this is not too bad. How could we compute this quickly? What would we use? We talked about this method. Because we can't do P minus 1 factorial quickly. That's painful. But we could actually calculate something to a high power. What do we use to calculate high powers quickly? I'm sorry? Well, we're going to use that in a moment as to what this should be. But how would I actually raise A to a huge power? Let's say the prime is of size 10 to the 200. Yeah, I would use fast multiplication. I'd use binary expansions. So because of binary expansion, this is doable. This is going to be extremely important when we get to RSA. This is why the Germans felt their Enigma was unbreakable. The amount of computational power needed to crack Enigma was so beyond any human possibility that the Germans were they felt extremely confident that they could communicate in secret. They made some very small mistakes in implementing their code. And those small mistakes made it from an almost impossible problem to a possible problem. So you have to really think about, can you actually do this? We cannot compute factorials fast enough to be useful, but we can do this. Now, as was remarked, by Fermat's little theorem, we know A to the P minus 1 is congruent to 1 mod P. So A to the P minus 1 minus 1 is congruent to 0 mod P. Well, we can then factor this. What do you know about the number P minus 1? Even. So we should probably put in, as always, P is at least 3. So we would get A to the P minus 1 over 2 minus 1, A to the P minus 1 over 2 plus 1 is congruent to 0 mod P. We're just using the difference of squares. If I gave you x squared minus 1, you would factor it as x minus 1, x plus 1. The only difference is the role of x is now being played by A to the P minus 1 over 2. Because P is prime, either this is 0 or this is 0. Right? So you can now begin to see where Euler's criterion is coming into play. This only takes on 2 possible values. So we get A to the P minus 1 over 2 is either 1 or minus 1 if A is not congruent, if A does not equal 0 mod P. So it at least takes on the same values as the Legendre symbol. Now we just have to show that it takes on the right values. What do you think might be useful to finish the proof? What could be useful? So we have some A in Z mod PZ star. What might be useful to finish the proof? Maybe that it's cyclic. Yeah, this is 1 G squared, G to the P minus 1, P minus 2. So we know A is equal to G to the L for some L. If L equals 2M, then A to the P minus 1 over 2 is G to the 2L to the P minus 1 over 2, right? Which is going to be G to the P minus 1 to the L. But what is G to the P minus 1? It's just 1. Equals 1 mod p. So we know that if a is g to the L, it solves this relation, and we now know that the Legendre symbol is 1, and it's a square, because it's even. And Euler's criterion is 1. So we've now finished the case where if a is g to the L for L even, the Euler's criterion says +1, and the Legendre symbol says +1. So they align in that case. Now we have to do what would happen if L equals 2m plus 1, not a square. And then I'll just leave it to you to finish and go through the calculation and see that you'd also get -1 in that case for the Euler criterion. The other way of looking at it is we know a to the p minus 1 over 2 equals 1 has at most p minus 1 over 2 solutions. We've already found p minus 1 over 2 solutions. So you could also count solutions. Okay. So this is really all I want to do from chapter 3. This is why we were supposed to have done the chapter 3 reading last week. You're supposed to be reading chapter 4 now. We're now moving to chapter 4 and encryption. This is, in my mind, the high point of the course, seeing why we care about stuff like this.